Good morning, welcome to new lecture. Today I will look at two different topics. First topic I would like to cover it is stresses on an inclined plane. Assume you have one rod we apply tension to this rod and cross-sectional area perpendicular to the rod it is A, again Young modulus it is E, and the length of the rod it is L. If we cut this rod perpendicular to rod, in this section, perpendicular I call N prime, we will have only normal stress. So if I cut it, because if this is external load P, in order to have equilibrium, I have internal force P here. P divided by A, cross-sectional area, will give us normal stress, and we will not have any shear stress in this surface. Let's see if we cut it this with one inclined plane, something like this, and this plane I call it M prime. What will happen? If I cut that with inclined plane, if I look at two free body diagram, here, this is P, this is inclined plane, M prime. Again, internal force, if this is X direction, this is Y direction, internal force will be P in X direction, in axial direction. This force will be P. Assume the angle of this plane, with vertical plane it is theta. So this angle is theta. If the cross-sectional area was A, the area for this plane will be, I show with A prime, and A prime will be equal to this area, it is A, so A prime area will be A divided by cosine theta. If I decompose force to the perpendicular direction to the plane and tangent direction to the plane, what I will have, if this angle is theta, this will be theta. So if I decompose P in Y direction, it will be P cosine theta, and component of the P in the X direction will be P sine theta. So normal stress in that plane will be normal force, which is P cosine theta divided by area. Area here is A divided by cosine theta, because area for that section is A prime. From here, normal stress will be P over A cosine square theta. How about shear stress? Here, because we have force tangent to this area, tangent to that plane, tau in that plane will be tangent force P sine theta divided by area, which is equal to A divided by cosine theta. From here, shear stress will be P over A sine theta cosine theta. If I summarize this, if we have rod subjected to, for example, axial force P, if I cut perpendicular to that rod, we will have only normal stress, which is, it is equal normal force P divided by cross section A. But in all other planes, if they make angle, for example, theta with that plane, we will have normal stress, which is equal to P divided by A cosine squared theta. In the same time, we will have shear stress. Shear stress will be equal to P over A sine theta cosine theta. So, this was the first topic I covered today, stresses on an inclined plane like prime. So in those planes we will have both stress. We will have normal stress, sigma. We will have shear stress, tau. And now we know how we can calculate those. Let's look at another topic, transverse shear stress. Transverse shear stress. If we have beam element, if we have beam, one segment of the beam, in this segment, if I show internal forces, assume this is y direction, this is z direction, and this is x axial direction. In beam element, usually we will have shear force and bending moment. Shear force V. In other side, if I show V, because the length of this segment, it is delta x. If here is V, here it will varies V plus delta V. And here if we have bending moment M, here we will have bending moment respect to the Z, and I call that M plus delta M. If I show that in 2 dimensions, this is segment of the beam, the length is delta x, shear force V, bending moment M, shear force V plus delta V, bending moment M plus delta M in general case. If I cut one small element out of this segment, the length of this, I cut it like this. And let's even, I cut like this entire. If I cut a small element, very small differential element, and the length is dx. I show that element here one more time. Stress on these element, stress on this element, assume this is neutral axis location, and we will have bending stress here sigma x, and in other side sigma x plus delta sigma x, because other side moment it is dm greater, so the stress will be sigma x plus d sigma x, and we have on top side stress, compressive stress, sigma x plus delta sigma x, and this is sigma x. If I take one small strip from this element and I look at to equilibrium of this shadow part like this, I'm writing equilibrium equation for this strip, for this shadow part, and I show with blue here. If I look at the equilibrium of that in the x direction, what I will have here, the height, for example, the area, not height, the area, this is neutral axis location, and this is that part. The area for this part in cross section I show with dA, and the width of this beam, assume it is B, so width of beam it is B. In order to have that in equilibrium, I will need shear stress in this direction. I show those shear stress with tau. So if I write equilibrium equation in horizontal direction, I will have sigma x times dA, sigma x times dA, it will be in positive x direction, plus tau times dx, tau times dx times width of the beam perpendicular to the board, that is B, minus sigma x plus delta sigma x times dA should be equal to 0. So sigma x times dA, force in the positive direction, minus sigma x plus delta sigma x dA, force in negative direction. Tau is tangent to this surface. That surface length is dx. Another side which is perpendicular to the board, it is B. So equilibrium equation, summation of forces in x direction for this blue part will be sigma x times dA plus tau dxb minus sigma x plus d sigma x dA is equal to 0. If I simplify this, I will have tau dxb minus delta minus d sigma x dA is equal to 0, because positive sigma x dA, negative sigma x dA, they will cancel each other. So if I simplify that, I can write like this. From here, I can write tau is equal to d sigma x dA divided by dxb. So if I take d sigma x dA to other side, I can write tau is equal to d sigma x dA divided by dx dm. I will continue here. From here, tau, what is d sigma x? D sigma x is bending stress. If I write in the bending stress term, can write dm y over I. Instead of d sigma x, I can write dm y over I, because you remember sigma was equal to m y over I. So d sigma will be equal to dm over dm times y over I. So from here I can write d sigma is equal to dm y over I. I put there times dA divided by dx b. From here I can write this dm over dx. Let's see, it will be dm over dx y dA I b. dm, derivative of moment respect to x, we know from static, derivative of moment respect to the x, we know from static, is equal to shear force. So instead of dm over dx, I can put v, so that will be equal to v shear force y times dA. Y times dA, area times distance, will be moment of area. Moment of area we used to show with Q in static. I, moment of inertia. B, the width of cross section. Finally, I can summarize this. Tau shear stress is equal to VQ IB. This formula has a lot of application, so we will use that formula a lot in mechanics of material. It is a well-known formula, and we will call it transverse shear stress. So again, one more time. If I remove all these, if we have one beam, cross section, for example, it is rectangular cross section, the width is B, the height is H, this is neutral axis location, shear stress, if it is subjected to shear force V, shear stress in this section we can calculate by VQ over IB. For example, if I want to find shear stress in this fiber, how? In this fiber, how in this fiber will be shear force V times Q, moment of area of all area above this fiber respect to neutral axis, divided by I, moment of inertia for this cross section respect to neutral axis, times B. B is width of the beam, and if I look at to this beam side view, and this fiber is here, for example, if I find tau here, we will have the same shear stress here, tau, because if I take a small element, if I have shear stress in cross section in the length, in order to have that element in equilibrium, in order to satisfy equilibrium, tau in the longitudinal direction shear stress, it should be equal, and again in other side we will have tau, and here we will have tau. So of course we will look at this later on. As a first example, let's look at the shear stress distribution in rectangular cross section. Again, we have rectangular cross section for the beam. The width is the B. Entire height it is H. Neutral axis will pass through centroid, so this will be H over 2, H over 2. We want, and this beam, this cross section is subjected to shear force V. We want to look at the shear stress distribution in entire this cross section to see how shear stress will distributed in this cross section. I take one small part of this cross section. I show that, for example, with dA. The distance from neutral axis I show this is y. The distance from neutral axis I show is y. Let's look at to see what is the shear stress distribution over there. If we write the shear stress distribution formula, it is VQ over IB. I for this beam, it is B H cube over 12. So instead of I can write B H cube over 12. The width of the section, it is B. V, it is shear force. Let's look at the Q. From neutral axis up to here, I assume it is Y. Entire height, it is H over 2. So this height I can show with H over 2 minus Y. Now, moment of area for that shadow part respect to neutral axis will be area for that H over 2 minus Y times B, area for this strip, times the distance between centroid of this up to here. The centroid of this, centroid, it will be there, it will be times Y plus H over 2 minus Y divided by 2. From here, if I simplify that, this will be 2y plus H over 2 minus Y. This will be Y plus H over 2 divided by 2. So instead of entire this, I can put 1 over 2 H over 2 plus Y. This times this, it will be h over 2 4 minus y squared b times 1 over 2. I can write this h over 2 squared minus y squared b over 2. So I can substitute here h over 2 squared minus y squared times b over 2. B and b, they will cancel. This 2 by this 12, it will be 6. Finally, I can simplify to the 6v h over 2 squared minus y squared over b h cubed. So, if I want to simplify everything, finally, I can write tau is equal to VQ over IB. For rectangular cross section, we can simplify to the V times h over 2 squared minus y squared over B h cubed. Now let's see what's happening. If y is equal to plus minus h over 2, plus minus h over 2 means we look at to the shear stress in these extreme fiber, in top fiber here, in bottom fiber here. In these two extreme fiber, if I put y plus minus h over 2, this term goes to the 0. So from here, tau will be equal to the 0. If I put y is equal to the 0, y is equal to 0 means the location of neutral axis here. In that case, shear stress will be 3v over 2bh. We know shear stress, average shear stress is equal to average one. Shear force V divided by cross-sectional area BH. Here this will be maximum one, 3 over 2 V over BH. So the maximum shear stress will take place for rectangular cross-section in the neutral axis location, and the magnitude will be 3 over 2 average shear stress or 1.5 average. So once I draw the shear stress distribution, average shear stress distribution is equal to shear force divided by cross-sectional area. But if I want to show real distribution, if I show the distribution with height in this graph, top side and bottom side, it will be 0. From 0, it will increase to the maximum value. The maximum value, it will be 3 over 2 V over BH, and it will take place in the location of the neutral axis location. And formula distribution is parabola 6V H over 2 square minus V squared over BH cube. If I look at the cross section, I show shear stress tangent to this with blue color. Close to the here, the shear stress is close to the 0. If we move from top to the neutral axis location, it will get bigger. And maximum will be in neutral axis location, and it will be symmetrical with respect to neutral axis. So again it gets smaller after we pass that line, much smaller. And it will reach close to the 0. If I show distribution will be something like this. From top to neutral axis, it will get bigger and bigger. After this, again, it gets smaller and smaller. 3 over 2 V over BH. Okay, I think for today it is enough. Thank you so much for watching this lecture. See you next session. Bye bye.